One of the needs of the industry involved with the fabrication of steel structures is to provide WPSs for the welding operations. As with any fabrication procedure, WPSs can have an impact on productivity and cost. The main purpose of this tutorial is to provide general guidelines to develop more competitive welding procedure specifications. Selection of a welding process can depend on several factors such as desired productivity, joint position, plate thickness, cost, or contract requirements. The type of joint is selected primarily based on design requirements. The type of joint penetration is also selected primarily based on design requirements. Joint penetration is classified as partial penetration or complete penetration. Depending on joint accessibility and design requirements, welds can be made from one side only or from both sides. There will be several available groove welds depending on the selected options. The geometric configuration of a groove should be carefully analyzed to achieve low-cost welding and desired weld quality. Joint details should be selected with groove dimensions that require the least amount of weld metal and still meet the specifications and fabrication requirements. Adjust root opening and groove angle to provide good root accessibility. These values determine how much weld metal will be required to fill the joint. Control of root pass thickness will avoid centerline cracking and slag inclusions and will ensure adequate fusion and penetration. Control of fill pass thickness after root pass will ensure adequate fusion. Maximum single pass layer width is required to ensure complete fusion throughout the cross-section of the weld and freedom from slag inclusion. The number of passes will affect notch toughness as bead size is related with heat input. As the number of passes increases, the amount of distortion and residual stresses increases. A balance must be established between a few large passes and many small passes. Check AWS-D 1.1 Clause 5 and AWS-D 1.5 Clause 4 for pre-qualified groove welded joint details, allowable tolerances and restrictions based on welding process, joint position, and plate thickness. Base metal is specified by the engineer based on suitability for the intended purpose. All base metals approved by welding codes are weldable. Some base metals require special welding materials and welding procedures. Generally, filler metal is selected to match the mechanical properties of the base metal. Depending on the selected material and project specifications, it will be necessary to consider other requirements such as corrosion resistance, hydrogen content, heat input control, stress relief heat treatment, joint position, and plate thickness. Check applicable AWS filler metal specification for description and intended use of welding consumables, and project specifications for special weld metal requirements. Welding variables such as amperage, voltage, and travel speed will have a major effect on the quality of the deposited weld metal and productivity. Strength, ductility, toughness, and heat input are dependent on the control of welding variables. Selected amperage, wire feed speed will determine the deposition rate used to fill the joint. Adjust welding variables within the range recommended by the filler metal manufacturer, suitability for actual fabrication, and code requirements. Some project specifications put some restrictions on the heat input to control toughness and hardness of the heat-affected zone. In general, high heat input results in lower notch toughness, and low heat inputs may increase the hardness. The combination of welding variables to compute the heat input can produce values that don't exceed the required heat input, but it does not necessarily mean that the welds produced using these values will be sound, or that they are applicable for actual fabrication. Check AWS-D 1.1 Clause 5 and AWS-D 1.5 Clause 6 for approved base metals, matching filler metals, and special welding materials for specific base metal and special applications. WPSs should not only comply with welding codes and project requirements, but must also maximize productivity and reduce welding costs. To find the most effective WPS, it is necessary to consider different options and run a provisional cost analysis to determine the WPS that uses the least amount of weld metal and minimum welding time. In the present case, 2 WPSs for the same conditions, but with different welding processes, FCAW and SMAW, were analyzed. Although the 2 WPSs use the same amount of weld metal, the FCAW process uses the minimum welding time due to its higher deposition rate, operating factor, and electrode efficiency. If a more accurate cost analysis is necessary, you can analyze in detail all the main variables involved in the cost analysis process, adjusting values according to experimental results or industry practices. Adjust welding variables range according to code requirements and experimental values. Preheat temperature depends on steel composition, material thickness, ambient temperature, degree of restraint of the joint, welding heat input, and diffusible hydrogen level of the weld metal. Check AWS-D 1.1, Clause 5, Table 5.8, and AWS-D 1.5 Clause 6, Table 6.3, for the required minimum preheat and interpass temperature. If the WPS complies with all the prequalification requirements of the applicable welding code, the WPS is prequalified. The use of prequalified joints and WPSs does not necessarily guarantee sound welds. Qualified personnel, welding engineering judgment, and fabrication capability is still required. WPSs may be required to be qualified by tests due to deviations from the pre-qualified requirements of the applicable welding code or due to contract requirements. Depending on the complexity of the project, WPSs will require a more detailed engineering analysis before they are approved for actual fabrication.